Hi everyone, in this video I'll show you a calculation that relates temperature with resistance of a piece of metal. This relation is fairly straightforward, that I represented here in the corner here. Resistance goes up when the temperature rises and resistance drops down when the temperature goes down. Fairly straightforward. So if you have an electrical circuit or a motor or a light bulb, whatever, and it's operating at an initial temperature of something, and the temperature goes up during the day or whatever, in normal operating condition things heat up, that means the resistance also goes up of the this metal load in a circuit. But it also could be just the wire itself, and if you take the wire or the light bulb or a motor outside and temperature drops from a reference temperature where, say, when the motor started up or whatever, and the temperature goes down, the resistance will also go down, making the operation more efficient. Less resistance means more efficient operation. The calculation I'm going to show you in three different versions. One basic equation, and I'm going to transpose it into three different formats. It's going to be fairly straightforward, just like this here is fairly straightforward, but there are some tricks along the way, and we'll start with two notes here. I'm going to use two Greek letters. No industry uses two Greek letters. One of them looks like this goldfish cracker here. That's a Greek letter alpha. And that what's abbreviated by it is that we're going to use an alpha number, which is the temperature coefficient of resistance of copper in this case. You can do aluminum, whatever suits your fancy, molybdenum if you have molybdenum wire, but what's important is that this alpha number is specific to a metal. It doesn't have a unit of measure, it's a percentage number. Okay, so it's a percentage doesn't have a unit of measure. End of story there. The other Greek letter is gonna be this triangle here. That's another Greek letter. I'm not gonna tell you the story why Greek letters, it is just so. So this one is delta, and delta means difference of, just in general, it means the business of subtraction. So difference of temperature is gonna be delta T. So difference of temperature is that you have, say, an outside temperature of minus 20 and an inside temperature of plus 20. So you have a difference of temperature in 40 degrees. Whether it's Celsius or Fahrenheit, it doesn't matter in this case. However, this alpha number, it does matter. This alpha number of about copper is, in this calculation example, relates to Celsius, degrees, metric. So even if you're doing, it comes from the North American electrical code, okay, the NEC or the Canadian code or anything North American. So both of them are actually working with the alpha number has or relates to Celsius degrees. Okay, so if you have Fahrenheit, you're gonna have to convert that first into Celsius degrees. How the equation looks like is fairly straightforward. Like I said, here is difference in or difference of resistance. You have an initial resistance, say 20. You have a difference in resistance of 10, so therefore you will have a final resistance of 30. Okay, 20 plus the 10 is 30. So that's how this Greek letter delta works. Fairly straightforward. The equation is this one that I'm going to be manipulating, but this is also used. They're both side by side for a reason, because like I said, this whole equation that is chopped up into two portions because it's easier to get it this way, relates and helps calculate at what temperature what kind of resistance are we getting out of a machine, or if we have some fixed resistances measured at operating temperature and cold, then we can calculate temperatures if we need to. So I'm going to show you some of these variations. Let's get going. In this first example here, I have an initial resistance of 150 ohms, say on a motor, something like that. You have this alpha number for copper, that Cu is copper, and it's 0.00393. You have an initial temperature and a final temperature there. Say the motor starts operating at 20 degrees, keeps running or heats up to operating temperature. At a higher temperature, it's going to have a higher resistance. What is that resistance going to be? What's the final resistance? A couple of notes here. Initial resistance is Ri. Some people abbreviate it as Ro, resistance original, or temperature original, or temperature reference, resistance reference. So there are some variations, but it's all the same. Okay, I like I and F because the TO looks like the little O looks like a 0. I don't want another symbol here that looks like a 0, so I don't use O. And T ref is just too many letters to write. I'm lazy, so I'm using TI and TF, RI and RF. Okay. One more thing about this alpha number of copper. In the NEC, this alpha number is featured at the bottom of this table. This is chapter 9, table 8. It's a tiny print. So here is chapter 9. Here is table 8. It says conductor properties and it has circular mills. And if you go down to the footnotes, you can see an alpha number of copper right around there. And it's 0.00323. And we have 0.00393. So what figures? I'll tell you what. This NEC is calculated at a 75 Celsius degree resistance. Okay, and on this figure comes from when copper is at 20 degrees, because this alpha number, although it kind of looks like a constant, it's not really a constant. Like I said, it's a percentage number. So as temperature rises, this number changes ever so slightly. So 393, 323, and there are other variations of this number. It's important to know before you start how is your answer key made up, if you have an answer key and you want to do well on a quiz. Okay, so just watch out for this alpha number. Here is another page I printed off. It's from NIST's website. It's this original work by J.H. Dellinger was filed with the American Bureau of Standards in 1910. And in this work, they made measurements on this temperature coefficient of copper. And you can see that the alpha number, they calculated it at 0 degrees Celsius, at 15 degrees Celsius, 20 degrees Celsius, and 25 degrees Celsius. And the figures are all similar depending on how clean the copper is, how much previous bending it went through, whether the copper is annealed or not, hard drawn, or however it was manufactured. If copper was never melted, it changes this alpha number slightly. You can see that they all are around the 00393-ish, but as temperature drops, this number gets bigger. So the alpha number rises as the temperature drops. So that's an inverse proportion relation there. So all of these decimal numbers in the table here are unique to copper only and are a result of one property of copper or metals, resistivity, or the inverse of resistivity, conductivity. Okay? And that's a completely different video. Resistance is not resistivity and conductivity is not conductance. Those are different things and different video. Also, why these numbers rise as the temperature drops is a completely different video and has to do with math. I'm not going to bother with it. We're going back to the original relationship here, that as temperature drops, resistance drops. So much so that if temperature drops down to absolute zero, you will have practically no resistance whatsoever. Some materials near absolute zero completely lose any resistance. They are called superconductors. So this relationship is valid. Don't be bothered by the alpha number. The alpha number is not resistance. All right? The alpha number is the temperature coefficient of commercial copper, there. Oh, one more thing. The original author Dillinger bolded this number here, 0.00394. I pre-printed my sheet with 0.00393 because NIST, or the American Bureau of Standards, revisited these figures since 1910, and they thought 0.00393 is a better number to use with copper at 20 degrees. It's a microscopic difference, don't worry about it. So let's do some math. Oh, before we do some math, I printed my sheets so that multiplication is indicated with center dots. I didn't want to go with X's because they look like alpha already, so didn't want confusion there. So now I have dots. I also have decimal dots, but I have center dots for multiplication. Okay, let's do some math. From here on it's fairly straightforward. This is the basic form of the equation. This, especially put your eyes on this one. What you have here is three numbers here are multiplied to get a fourth one. And once you have this fourth one, you add it to the initial resistance. It's fairly straightforward. So that's two multiplications to do and one addition. So it doesn't get much simpler than that. So what you do on a calculator, of course, enter everything. 150 is the initial resistance there, times it by this number then, 00393, and multiply it by delta T. Delta T is the difference in temperature. Oh, we don't have difference in temperature calculated. It needs to come after this final temperature, initial temperature. Very straightforward. Delta T is always calculated as temperature final minus temperature initial. Always final first. If this 50 was, say, 0 degrees, you would still need the 0 would be up top. 0 minus 20 equals minus 20. Okay, so temperature, this difference in temperature, this can be a negative number. In this case, it's a positive 30. Okay, 50 minus 20. So that 30 plugs into here in the equation. So I'm just gonna go times 30 equals, we've got 100, we've got, for difference in resistance is 17.685 ohms. And like this little equation here shows, this one here, what we need to do with this 17, you have to add it to the 150, that was the R initial, to get your R final, which is going to be 167.685 ohms. Fairly straightforward. On the next version, so this is the most intuitive because it's three numbers multiplied. Just grab the numbers, plug and chuck. On the next version, if we have, say, this number here, and we want to calculate final temperature, this is how the situation looks like. This basic equation needs to be transposed, and to calculate final temperature you need this form of the same equation. So this is just after this one being transposed. So in this situation we have a final resistance and an initial resistance given. Say a motor was measured cold, it was 150, it was measured hot, it was 165. And I kept the temperature and the motor resistance numbers the same. Instead of 167.6, I just went with 165, just like so. So let's see if we get something around 50 degrees-ish, we need to get back when we calculate the final temperature. It's going to be comparable. So what needs to be done is delta R, the difference in resistance, needs to be divided by the product of these two numbers. These two numbers are here, they're easy to multiply, but we need to calculate here the difference in resistance. It's fairly straightforward. 160 minus 150 is going to be 15 ohms. So what you do is the 15 ohms goes here. So in a calculator, go 15 divided by, and then open a bracket, or otherwise you have to use the memory function of the calculator. Ri was 150 times this alpha number for the copper, that one there, to get us a total of 25.44. Our delta T is 25.44 degrees Celsius. And to get our final temperature final, we need to get this difference added to the initial. So we just add the 20 to it. So that's 45.44 degrees Celsius. Celsius there. So that's kind of close. Just for comparing, and that's why I went with almost the same numbers from calculation 1 and calculation 2, is because the 150, the 165, the 20 and the 45 are kind of close to the 20. Instead of 45 it's 50, the 150, and the one instead of 165 it's a 167. So you get the idea that these calculations both work, and the results are comparable. Last version on this one. What if we need to calculate out of this basic equation, say this one, the initial resistance of something? That's another transposing of an equation. So this again is the original equation, and this is how it looks like when you want to calculate the initial resistance. It's not much different from the previous version. I'm just going to do this. Okay, look at it. Maybe pull that piece of paper out. Look at the two of them here. Delta R is up top in the numerator position. Alpha is down here in both cases. And basically delta T and Ri trade places. Delta T and Ri just basically trade places. Okay, that's the only difference between the two equations. So calculation from here on is very straightforward. We have a delta R to enter into the calculator, which is over here 17. I picked 17 because in the first calculation our resistance was, delta R was kind of close to 17. So we'll see what we get back for Ri in this case. We're gonna need to get something close to 150. Let's see how close we get. So 17 is in the calculator, divided by, bracket open. We need the alpha and we need delta T. Delta T, we don't have delta T, the same stuff. Delta T is calculated by TF minus TI. So that's 50 minus 20, that's going to be 30. I kept that one the same, so you can check that all of these calculations work or are equally valid. So 30 times 0.00393, close the bracket, equals 144 ohms. So we have an initial resistance of 144.1 ohms there. What this means is that if the temperature rises from 20 degrees to 50 degrees, then the resistance goes from 144 to 144 plus 17, okay, to that number. So that's how to use these equations, all of these three variants to it. Now by far the easiest to memorize is this. So I have here a memory jogger, how these other two forms can be somewhat better memorized. So just disregard the fact that alpha is this crazy decimal number here. Just plug in easy numbers, say 2, 3, and 4. You know that the multiples of 2 times 3 times 4, 2 by 3 is 6, times 4 is 24, that's going to be 24. Okay, so Ri now is 2, alpha is 3, delta T is 4, and delta R is 24. It doesn't matter for now that this one usually needs to be a big number and not is a small number. Just ignore that fact. But bottom line here is 3 numbers are multiplied to get a fourth one. So if we want to calculate delta T, which is 4, how can we get a result of 4 using the remaining digits 2, 3, and 24? Well, the biggest number, the 24, needs to be divided by the multiple of 2 and 3. That was 2 and that was 3. So 24 divided by 6 is 4. And of course the same works on this one. 24 divided by, the alpha number was 3 and the additive was 4. Yeah, 24 divided by 12 is 2. Okay, so the 2, 3 and 4, yeah, I didn't want to pick 1, 2 and 3 just in case one of them repeats or whatever, but some easy numbers. So that's how you can make sure that, or one way to make sure that what you think you remember correctly is actually correct. You know, this is something you can do. Thank you very much for watching. That's what I wanted to share about how temperature and resistance relate and how you can calculate some of the temperature changes and resistance changes that happen in normal operation in electrical circuits.